son as a secretary. He's disappeared. He is coming.
He's going to give his notice if he's upstairs.
Good evening, welcome everybody to the opening meeting of the Astronomical Society of Glasgow for the 2024-25 season. Unfortunately, Andrew can't make it tonight, so I'm standing in for him to do the opening and all the rest of it. So the first thing is, I'll hand it over to David to do the Secretary's announcements.
Good evening everyone, welcome to the first meeting of the new session. There's quite a lot happening already to start off. First thing taking place is actually a very important event which is taking place this coming Monday, which is the Society AGM. So that's at 7 PM and it's being held via Zoom. So we would encourage you to join that if you can log on and join the meeting. The next event is taking place a week tonight, which is the next meeting of the imaging group. Again, this is a Zoom meeting. The time is 7:30 to 9 PM. I think if you want to know any details, I think Sinclair is here tonight. Sinclair is over there.
Yeah, I'll send out an email a couple of days before, but I emailed Bob Coates today, who's one of our members, and he's building a remote observatory in La Palma. So he'll be telling us a bit about that. And I've seen a kind of, he's got a kind of prototype of what the original at the moment. It looks like a huge minibar, and that contains an extended pier, 2 telescopes in the mount. So he'll be explaining,
Okay, that's great.
talking us through that next week.
Okay, sounds good. And then the week after we have the first of our ASG members' nights at Etmo. That's the Tuesday, 1st of October, 7:30 to 9 PM. So that's a members' event. The next event after that takes place on Monday the 7th of October, ASG Public Night at Murdoch. Again, that's a paid event, so again, 7:30 to 9 PM. Following that, we have the first meeting of the Observers Group, which is run by Robert. What will be about?
Well, we'll be talking about what's visible in the night sky in October, what's happening in the sky, and there's stuff about the planets and the moon.
Right, okay, that's it. And again, that's a Zoom event.
Yeah, so much.
So that's 7:30 to 9 PM. Following that, we have the first of our Acre Road nights at the Acre Road Observatory, which runs alongside the beginners class, which Chris and Warner will be running.
That's the second Thursday.
The second Thursday, 10th of October.
That'll be Acre Road, which is for absolute beginners. Beginners astronomy 101 in person.
And then just a couple of reminders. Membership fees can be paid now. This allows you to access to all the various members' benefits. Our membership secretary isn't here tonight, but you can join online. If you go onto the website, you can join that way. And finally, a reminder that the deadline for calendar images for the 2025 calendar, the Society calendar, the deadline for that is tomorrow, and I think it's Chris and Warner that's taking the emails, is it?
What's that?
For the images for the calendar?
The images for the calendar will be in by
Tomorrow.
the 30th.
No, tomorrow.
Right, okay. Then we got any astro images for consideration for this year's calendar. Please get them in the sharpish. Okay. Send them to Andrew Conway.
Okay, that's it.
leads us now to our main event tonight. I'm very honoured to have Dr. Alex Hall from the Royal Observatory of Blackfoot Hills. He's going to give us a talk about exploring the dark universe with the Euclid Space telescopes.
Thank you. Well, thanks very much for the invitation. It's a pleasure to be here to talk to you about this amazing mission called Euclid. I'm Alex Hall. I'm from the University of Edinburgh, based at the observatory on Blackfoot Hill in Edinburgh. So just to plan this talk, I'm going to start by introducing the Euclid Space telescope. I'm going to describe what it's for, why we need another space telescope. I'll present some early results from the mission, and then finally I'll talk about some of the prospects for the future, describe some of the things that we hope to get out of this amazing piece of technology. So, I just want to give a little bit of a brief bio about myself first. So I'm originally from the Isle of Man. Anyone from the Isle of Man in the room? No. Sometimes someone sticks their hand up, doesn't happen very often. But I went to uni in England, did my PhD there, and then about 11 years ago moved to Edinburgh, beautiful city. There's the observatory. If you've not been to the observatory in Edinburgh on Blackfoot Hill, it's a beautiful old Victorian building. We're actually having our doors open weekend next weekend, the weekend after this one. So there'll be an opportunity to go and visit the observatory. If you haven't done that before, it's really worth doing. But you should get your tickets early because it's a really, really popular event. Okay, so I'm a cosmologist, which means I study the universe as a whole, its history, its large-scale behaviour, its evolution, its future. And in practice, that means I do a lot of maths, I do a lot of computing. Here's me. I think this was taken during the pandemic. I was working from home a lot. I do a lot of kind of mathematical modelling. I have a lot of bad ideas. All the bad ideas end up in that waste paper basket. It's a lot more full now than it was then. But it's a really great job. It's a really great privilege to be able to do this. And a lot of my work now is focused on this mission. So this is Euclid. It's a European Space Agency space telescope. This is a picture of it when it was in the lab. I think this photo is taken in Cannes in the south of France. There's the sort of obligatory human for scale. So a little bit of sort of technical specification first. So this is an ESA mission. Inside we've got a 3-mirror telescope, Corche telescope optical system. It's got a 1.2 metre diameter primary mirror. So this thing is about just over a metre across. There's 2 cameras inside. I'll talk a bit about those in a second. The thing stands 4.7 metres tall, weighs about 2 tonnes. The initial budget for this mission was about half a billion euros. That's classed as a medium-sized mission by ESA. But when you add up all the kind of costs of the salaries for everyone and all the investment from national space agencies, etc., the true cost is more likely to be around 1 billion euros. Why is it called Euclid? It's named after this man, Euclid of Alexandria, who was an ancient Greek mathematician who lived around 300 BC. And Euclid is most famous for this treatise on geometry called The Elements, which for a very long time, for over 1,000 years, well over 1,000 years, was the standard textbook to teach the Western world geometry. So geometry, that's the laws of parallel lines, triangles, angles, these kind of very sort of basic concepts that we sort of learn at quite a young age. And the reason we've named it after Euclid is because the mission is trying to explore the geometry of the whole universe. So the geometry of the 4-dimensional surface called space-time. Okay? I'll explain a little bit more about that later. Okay, so Euclid was launched last year on the 1st of July. Launched on a SpaceX Falcon 9 rocket from Cape Canaveral in Florida. If you were following the news at the time, we had a lot of trouble with finding a launch vehicle. Originally, we were meant to be on the Ariane 5 rocket, the European rocket. Actually, before that, we were meant to be on the Soyuz rocket, but then Russia pulled out, of course, from after the war in Ukraine. So we couldn't use the Soyuz rocket, we used the Ariane rocket, that was oversubscribed, we couldn't get a spot on the European rocket. The next iteration of Ariane, which was Ariane 6, we couldn't get on that either. But SpaceX came along and helped us out, and I have got to show you the video of the launch because I think it's spectacular. So there we go. 3, 2, 1. Weather was perfect, sunny day.
Falcon 9 has successfully lifted off from pad 40 and throttled down to prepare for max Q, which is coming up at T plus 1 minute. 1 minute and about 12 seconds.
So it's very nerve-wracking watching that because, I mean, this is decades of people's work and career, and we've basically taken it and strapped it to a huge bomb and then exploded it into space. So this is, yeah, a very heart-and-mouth moment. One of the reasons SpaceX was a good option was because it was actually cheaper to launch on SpaceX rockets compared to the European rockets. And part of the reason for that is because of the fact that the primary stage is reusable. So here what you're seeing, on the right-hand side is a camera mounted to the top of the rocket.
And on your right-hand screen, you can see that the MVAC engine.
On the left is a camera on the lower half of the rocket, which is separated now. So Euclid, the satellite is on is in the top of the rocket, so that's flying off. The lower part is falling back down to Earth, and we'll get a camera view now of the lower half of the rocket falling back down to Earth, and you'll see the Atlantic Ocean come into view.
This mission, and that
So
is
left-hand side.
in just a few seconds, followed by the landing burn about 20 seconds after that.
And if you watch this, you'll start to see a landing pad come into view, kind of moored out in the ocean. I think this is maybe one of the most impressive things I've ever seen. So essentially, you're kind of manoeuvring a stick.
And you can see that the
And
engine
through the
has shut
atmosphere.
down and the landing burn has begun on the first stage vehicle.
Here's the camera view from the landing pad on the right. There it is. I think that's amazing. Incredible. So yeah, the SpaceX people really, they really know their stuff, and the launch was exceptional in terms of its precision. So of course, once that stage separates and once the satellite goes off, we've got a few micro thrusters on board, but the trajectory is really fixed by that initial launch. It was very precise. So what happened after launch? So Euclid travelled out to a part of space called Lagrange Point 2, L2, which is about 1.5 million kilometres from Earth. It's not a fixed point in space, it's orbiting around the Sun with the Earth. And this is a really popular place to put space telescopes. And the reason for that is because it's a very thermally stable part of space. The Earth and the Sun are always in the same part of the sky from the point of view of the satellite. That means the temperature doesn't change very much with time. It also means that you can just point the telescope away from Earth and Sun, and you never have to worry about them. So James Webb Space Telescope, a lot of the other European and NASA telescopes are all in the vicinity of Lagrange Point 2. So it took about a month for Euclid to get there. So let me just describe some of the kind of technology that's inside this thing. So there's a picture of the mirror. As I said, it's about 1 metre across. Little technical diagram on the right if you're interested, but it's essentially, it's like any other telescope really, a reflector. We've got a primary mirror, the light comes in through the top, bounces off the primary mirror, bounces back off the secondary, goes through a little aperture. There's an optical system where further focusing happens. Then the light gets split into near-infrared wavelengths and shorter optical wavelengths. So there's what's called a dichroic which splits off the light. Half the light goes into one camera, and the other half of the light is reflected off and goes into the other camera. The reason for this is because we've got multiple different science cases that we want to use this telescope for, and that requires different kinds of wavelengths. So first of all, let me talk about this one. This is the Visible Imager, or VIS. So this is one of Euclid's 2 cameras. The UK led the construction of this. It's a high-resolution camera, 600 megapixels. It's got a very wide field of view. Now this is important for the sort of science that Euclid does. Okay, so every image that Euclid takes is a very large image on the sky. I'll show you some sort of comparisons with other telescopes later on. It's very high resolution as well. So as well as having these big, wide pictures of each chunk of sky, we also get very fine detail. So every pixel can sort of subtend an angle of about 0.1 arc seconds. So we're getting very, very fine resolution. This camera is sensitive to optical wavelengths. As I said, the construction of this was led by the UK. It was mostly constructed at this place. This is the Euclid Space Science Laboratory, which is down in Surrey. The other camera on Euclid is called NISP. It stands for the Near Infrared Spectrometer and Photometer. This is led by France. So this is a big European-wide collaboration, but the sort of largest players are France and Italy and the UK. So this again is a very high-resolution camera, wide field of view, and gets the near-infrared wavelengths, so the kind of the redder end of the spectrum. So very quickly, very shortly after we launched, we started to get images down from the telescope, and this is one of the first images that we got. So on the left, I'm showing just an exposure of the camera. The little kind of squares you see are just the individual detectors. There are gaps between them just because of the way it's all constructed, right? But this is essentially just one picture that we got from a relatively short exposure time. If you want to get the sense of how big this is, there's the full moon scale. So every snapshot we take covers an area that's a little bit bigger than the full moon. The Hubble Space Telescope has a field of view of about this size, right? So we get comparable precision and angular resolution to Hubble, but Euclid has a much larger field of view. Okay, so that's the kind of real advantage. And the reason it has that is because we want to cover a very large portion of the sky. So Hubble, it's done great things for astronomy over the last 30 years or so, 35 years. But it is limited in the sense that it can only really stare at small patches. It can't get that kind of broad picture of the whole universe, which is what we want to do with Euclid, because it's a cosmology mission. We want to understand the very large-scale properties of the universe. Let's zoom in then on one of these patches. So this is just looking at that detector at the top there. Zooming in on the right. And very, very quickly, with very little sort of effort on behalf of the scientists or engineers, you start to see interesting things pop out. You see stars with the diffraction spikes. You see these beautiful galaxies. You see artifacts of the optics even. You see like little things like that, right? That's not real. That's just a sort of internal reflection, if you like, within the telescope. We also see little streaks, which are cosmic rays that are just battering the telescope all the time. These are high-energy particles flying around the solar system. Let's have a look at it in a bit more detail. Again, you see these cosmic rays. These are these streaks across the image. So if we want to get to the interesting stuff, which is the galaxies, so here's a beautiful spiral galaxy viewed face on here, and there's one viewed a bit more edge on. Clouds of stars, billions, hundreds of billions of stars swirling around a massive black hole, huge supermassive black hole at the centre. These are the targets for Euclid. So there's a lot of image processing that we need to do to correct these images for these streaks and these artifacts. But we know how to do that, and it's a well understood problem. I'll just show you the near infrared image as well. So in the near infrared, the universe looks sort of similar to how it looks like with your eyes in the visible wavelength range, but it looks different. There are differences. But again, you see beautiful galaxies pop out, and again, this is a really promising image. So Euclid is a survey to understand the whole universe, and in particular the expansion of the universe and dark energy. And I'll talk more about dark energy and the kind of dark aspects in a bit. But really to do this, we need to cover as much of the sky as possible. The dark universe, well, by its very nature, you can't see it. You have to tease out its existence by looking at a lot of galaxies. We need a lot of data to pick out this very subtle, small effects of the dark components of our universe. So we need lots and lots of galaxies, and essentially we're doing a survey. We're essentially going to map about 1/3 of the sky over the next 6 years, and we'll just take images and we'll count galaxies, we'll measure properties of each galaxy, so we'll measure how big it is, what shape it is, its coordinates on the sky, how far away it is, and essentially make a big spreadsheet. Okay? And that spreadsheet will have about 1.5 billion rows in it. And each row will be a galaxy, and each column will be some property of the galaxy. So we'll get a lot of data from this over the next 6 years. So this is going to be a huge resource for all of astronomy. So the way we do this is we build up data slowly. So we've already taken about, I think, 500 square degrees already, but the way that we sort of operate is by building up area. So this little kind of video shows how we do this. The galaxy, this is our Milky Way running across the middle of the diagram here. So we purposely avoid that because we want to look outside of the galaxy, outside of the Milky Way. We're interested in objects in the, sort of the deepest, far-flung regions of the universe. So we want to look away from the Milky Way. So we don't bother looking at anything in the plane of our galaxy. We also avoid this kind of faint band here. This is the plane of our solar system, the ecliptic plane. The reason we avoid that is because there's lots of dust in that plane. Okay, this is also called the zodiacal dust, which is sort of the emission from just like dust, like all the stuff that's kind of a remnant of the original disk that formed all the planets in our solar system. So this is a huge, massive undertaking. I mean, this is it's a partnership between many different organisations who have worked to pull this all together. So the Euclid Consortium is just, they're the scientists, that's people like me, but we've also worked with engineers, software developers, space scientists at ESA and the National Space Agencies. There's contracts with these aerospace companies who built the satellite and built the bits, and NASA as well. Just a little picture from one of our meetings, just to give you a sense of the scale of this. I mean, this is a relatively small turnout actually, but there's over 2,000 members of this consortium worldwide, in 17 countries. So this is it's like an organisational challenge, as much as it is a technological or scientific challenge. But the UK is a leading partner in this. So we're kind of one of the originators of this mission. So I think the UK should be very sort of proud of its role in this. Edinburgh in particular has invested a lot of time, a lot of person power over the years in kind of initiating this project. If you're wondering where all the money comes from, well, in the UK, all our funding comes from the UK Space Agency and the Government Research Council for Science and Technology, which is STFC. So they fund sort of most of the astronomy research in the UK. But this is ultimately coming from the UK government and from the UK taxpayer. We also get funding from ESA, European Space Agency, but again that's funded by the national member states. So it's that's sort of most of the kind of Western European countries. It's not sort of connected to the EU. It's kind of a separate thing. So this is it's coming from the taxpayer. Right, what's it for though? Really. So we want to measure the properties of dark energy, but we also want to understand what dark matter is. We want to measure the properties of fundamental particles called the neutrino. We want to test Einstein's theory of gravity. We want to probe the very earliest moments of the universe. So we're really asking the kind of biggest questions that you can ask in astronomy that deal with quite fundamental mysteries that are really important, not just in astronomy, but all of physics, really. So, how do we do this? Well, we make maps, essentially. We want to observe as much of the universe as possible. And of course, the further away, the deeper we observe, we're looking back into the universe's past. because the light has taken that long to get to us from these distant regions of the cosmos, that we're seeing the universe as it was in a younger state. And so by looking at the way that galaxies look like and the way that galaxies are distributed across the sky, as a function of distance, at different distances, we're actually probing the evolution of the universe. And we know the universe is evolving because we know the universe is actually expanding. And this little diagram is meant to kind of illustrate that. It's quite a confusing diagram, I think, because you've got to imagine that we're in the universe. It looks like from this picture that we're sort of outside it looking in, but of course the universe encompasses everything around us. But we think that about 14 or so billion years ago, the universe, everything in the universe was in a very compressed state called the Big Bang. We think that there was some kind of cataclysmic, explosive event that happened, and in that event, everything that we see around us was sort of created. All of the particles were created. We don't understand this event very well. We don't know if anything came before this or what that question even means. But we do think that this happened. Now, shortly after the Big Bang, the universe is expanding. All that really means is that stuff is getting further away from each other all the time. So all the sort of distances between things are kind of getting stretched out and getting longer and wider all the time. And in that process, the universe starts to cool down. In those early days after the Big Bang, it's a very hot, dense, kind of violent place. And soon after the Big Bang, this starts to cool down. And what happens is that atoms then form. It takes about 300 or 400,000 years for that to happen. But as this sort of gas, this plasma, primordial plasma cools, atoms form. It takes a little longer for stars to form. We think that the first stars started to form about 400 million years after the Big Bang. It takes even longer to form the first galaxies and planets, but eventually gravity takes hold, gravity pulls things together, we get gravitational collapse, and then we start to see galaxies, the universe as we know it today, start to emerge. Okay? Now you'll notice that this diagram is kind of flared. So you see that it sort of starts to flare out around here. What this is meant to represent is that the expansion of the universe suddenly starts to accelerate around 7 billion years ago. And this is totally unexpected. So the Big Bang, since the Big Bang, the universe has always been expanding, but for much of its history, that expansion was getting slower and slower. So it's still expanding, but sort of plateauing off. About 7 billion years ago, when the universe is about half its current age, that expansion begins to accelerate. Suddenly gets faster and faster. And this is one of the most serious mysteries, one of the biggest mysteries in astronomy, is why this started to happen. And we've invented this substance called dark energy to explain this, inverted commas, because it's not really an explanation. It's just a new thing that we put into the theory by hand to give you behaviour like this. But if this stuff is real, if this dark energy is real, it's got to be like nothing else we know. It can't be normal matter. It's not like the elements in the periodic table. It's not even like dark matter. It's something very, very poorly understood. It's some new phase of matter, of energy. So figuring out what the nature of this dark energy is one of Euclid's main aims. And we know that this stuff, we think this stuff exists. We know that acceleration is happening. We've known this since the late 90s. This has led to the Nobel Prize in the early 2000s. And we have a sort of rough understanding of this stuff, this dark energy stuff at sort of 10% level, but with Euclid we're aiming to really get more precise and understand it at the 1% level. Okay, so dark matter. So, you may have heard of another dark substance, dark matter. How is it related to dark energy? Well, we think it's quite different. We think it's quite distinct. We think that dark energy does not clump together. So dark energy is like a kind of anti-gravity force almost. It's pulling things apart. It's driving that acceleration in the expansion of the universe. Dark matter, on the other hand, does clump together. We do know this. We think it interacts with itself through gravity. So if you've got a region of the universe with a blob of dark matter, more dark matter will start to fall in, be attracted into that blob, and the blob will get larger and larger, and you start to get these big kind of big globules kind of congealing out of the initial kind of state of the universe. So we think dark matter behaves in this way. All the dark matter really is, it behaves almost like normal matter, but it's not luminous. We can't see it. We only just see its gravitational effects. So we can sort of see its impact indirectly, but we don't actually see it directly. What we also know is that combined dark matter and dark energy make up 75-ish% of the whole universe today. So dark matter we think makes up about 25%, dark energy about 70%. That leaves only about 5% for normal matter, so the stuff that makes up stars and gas and planets and all the kind of materials that we're familiar with. So 95% of the universe is dark, and this is a big problem for physics. To explain this, what are these things? How do they fit in with our picture of how the universe works? So Euclid is a mission, a purpose-built mission to understand these things. We want to essentially see the invisible universe by making maps of dark matter, and with those maps understand the way the universe is expanding and tease out this information about dark energy. And along the way, we'll hope to get some clues about the initial conditions of our universe and the Big Bang. Okay, but how do we actually do this in practice? I've just told you that you can't see dark matter. How on earth would you make a map of dark matter when it's invisible? Okay, so we've got to first of all look outside of our galaxy. So this is the Milky Way on a clear night. But we're not interested in that. We want to go in between the stars. We want to look into deep space. So here's a very long exposure of a very sort of pristine, clear patch of sky. This is a Hubble Space Telescope image. This is the Hubble Deep Field. And what you see is galaxies everywhere. And these galaxies are very similar to our own Milky Way. And they come in all different shapes and sizes, colours, properties. We see these spirals. We see sort of blobs. We see little faint things. Those are galaxies too. Okay, so our universe is absolutely chock full of these things. But if you zoom out of this picture and you take a region of the sky that's large enough, and you plot with a little coloured dot the position of every galaxy that you see, this is the kind of map that you get out. And this is a huge map. I mean, this is like 6 billion light years from across and about 4.5 from top to bottom. And every coloured dot in this diagram is a galaxy. Okay? So it just looks a bit fuzzy. I'm not sure you can really tell much from this. But what I want to convince you is that this is not just random. There is structure in this map. There are dark spots where there's not many galaxies. Okay? There are these kind of spots where there are many more galaxies. There are these kind of regions that seem to connect different parts of different hotspots, different clumps of galaxies. There's a lot of statistical information in maps like this that we can try to measure to understand the properties of our universe. And these kinds of maps will tell us about gravity, because gravity is driving a lot of this structure that we see. I'll come back to that. Another way that we measure the universe is through gravitational lensing. So as well as measuring the positions of galaxies and making those kind of maps, what we can do is look at very distant galaxies and look at how the matter in between us and those distant galaxies is affected by the gravity of the dark matter. So this is another famous Hubble image showing a cluster of galaxies. So this is a region of space where there's lots of galaxies all living close together. And what you can see, if you look carefully, is these kind of pronounced arc-like structures. Okay, see these? So these are background galaxies, so galaxies that are living behind this cluster at a much greater distance than this cluster. As the light has travelled from those galaxies to the telescope, it's not travelled in a straight line. It's gotten deflected by the gravitational pull of the matter that's all the matter that's in this kind of system that's in the foreground. And what that's done is it's created this very pronounced distortion of the light and bent the light into these images. And you also get multiple images. You see, actually, this little bit of arc and that bit of arc are the same galaxy. And the light has just been deflected in this very dramatic way. This is another cool example. So this smiley face is another dramatic example of gravitational lensing in action. So these are real images, okay? I mean, it looks almost fake, but this is what we actually see. And these are called Einstein rings, and they're examples of very pronounced gravitational lensing. Another way of understanding this is perhaps a more familiar example. So this is, it's a swimming pool, and we're looking from the top down onto the swimming pool, and we see the bottom of the pool, tiled in this kind of regular pattern. But you also see that as the light has bounced off the floor of the pool, it's been refracted by the water, and the water's got ripples on it, so there are regions of this where you see these distortions, right? It's not the grid anymore, you see strong distortions. In other areas it looks more gritty, it looks more like the real thing. And when we look at the universe, we're essentially looking at it through this kind of crinkled glass-like effect, because the gravity of all the material in the universe is affecting the way that the light travels through space. In exactly the same way as the swimming pool is affecting the light here. And you can even use the fact that there are parts of this grid that are really have pronounced distortions to work out what the height of the water is in that area, in that part of the pool. And in the same way, we can use the distortions of galaxies, the shapes of galaxies, or the pattern of images, to work out where there's more deflection happening, where there's more dark matter. So we can use the gravitational effect of dark matter to understand, where are there clumps, or where are the regions where there's relatively less dark matter. So this is what we'll do. So we're going to do this, and we're going to do it right back sort of 10 billion years ago. We're going to observe this chunk of the universe, so the most distant objects in our survey will be around sort of here. And by doing that, we sort of track the evolution of the universe. We follow this period where this expansion starts to accelerate. So we can really sort of follow how dark energy is impacting, affecting the growth of the universe. So we're going to make a map of dark matter using these techniques, gravitational lensing, and where the galaxies are, because the galaxies are meant to trace out the dark matter. So that where there's more dark matter, we think there are more galaxies. So the positions of galaxies can also tell us about where dark matter is. How do we kind of practically then learn about things like dark energy? Well, to do that, we need computer simulations. So the idea is that we have some prior understanding of how the universe should be evolving and how dark matter structures should change with time. And those models mostly come from very advanced computer simulations. And so I'm going to show you an example of that in this little video. So on the left of this slide, what you'll see is a simulation box of a big chunk of the universe. And I say big, this is like 100 million light years or so across. So we imagine that we're going to simulate the way that the universe evolves from an early time in its history to the present day. Now, early times, before stars had much of a chance to form, or galaxies had much of a chance to form, the universe was very smooth. So this kind of initial picture you see is actually quite smooth. It's grey, fairly featureless. Okay, there's little ripples that you can maybe see. So we do start off this simulation with little ripples. We think those actually originate from quantum fluctuations very, very close to the Big Bang. On the right-hand side, you'll see a zoom in of a small patch, but let's just set this going. Now, we're moving forward in time here, remember? And what you already can see is that gravity starts to pull things in. You can even see that on the right-hand side. You see these things moving in. So here there are dense parts of the universe. Things like fall into those dense regions, and you start to see this structure emerge. You see these dense spots, you see these blue spots where there's relatively less material, brighter spots where there's more material. You see these tendrils connecting things. You see this kind of web-like structure emerge. And this now starts to look a lot like our map of galaxies that we saw earlier, okay, with the dense spots with lots of galaxies and these kind of voids where there are fewer galaxies. So we can do a pretty good job, actually, of modelling the way the universe evolves and the way that galaxies are spread across the sky and the way the gravitational lensing happens and all those distortions can be modelled with quite high accuracy by simulations like this. But these simulations, they have free parameters. Okay? They have sort of knobs you can twiddle. They have different options that you can run them with. And those options are things like how much matter is there in the universe, how much dark energy is there in the universe, how fast is the universe expanding today, how clumpy is the universe at the start of its life. And so by twiddling those knobs, we can change the detailed patterns that we predict from these simulations, compare them with our data, and then that's how we can learn about what the actual values of these things are. So that's where those 25% dark matter, 70% dark energy numbers actually come from. So this is the way that we practically do this. We're comparing maps that we've made of the dark matter that we make using these amazing images of galaxies, and we compare them to models to work out how the universe has been expanding and thereby understand dark energy. We need Euclid to do this because we need to get these very fine details. Okay, I've shown you this image of these gravitational lens systems with these very pronounced arcs. You only see these if you have a very high resolution telescope. But you also need to get the kind of large scale features of the universe. Right? I told you this simulation box was 100 million light years across. So to map kind of these vast volumes of space, you need a telescope that can get you these big images, and you need to do it in as short a time as possible to make it economical and to sort of make sure you don't run out of micro thruster fuel. So you need something with a big field of view, basically. You need something with a big field of view, high resolution, and so Euclid has been purpose-built to do both those things. So I showed you this before, but this is the idea. You know, we do this over about 1/3 of the whole sky. It will take about 6 years to do. Let me show you some early results. So I don't have any kind of dark energy, fancy dark matter results to show you yet because we're still in the early days. We launched last year, and the survey only started in February this year. But let me show you some of the early results. So I mean, the first thing that we saw was pictures like this. Absolutely useless, right? What you're seeing here is the telescope wobbling around as the shutter was open. So you see like stars kind of, it looks like some kind of abstract art. The reason this has happened is because we had a stability issue on the telescope. So this was solved after a software update. We were actually able to upload a patch to the software on board the satellite. And now it's very stable, so we don't have this problem anymore. Another issue we have is ice contamination. Simple idea, there's water vapour that's gotten into the cavity of the telescope. It's frozen onto the mirrors, and it steams everything up. It clouds the vision of the telescope and gets in the way of the optics. So what ESA did to tackle that was essentially point the thing towards the sun to heat it up. And that worked brilliantly. So there's a diagram here showing heating starts here. This is the kind of the amount of light, the increase in the amount of light received after about 1 hour. After about an hour and a half, we start to see the light received go up. Okay, and it went back up to the original levels that we had just after launch. So this seems to have worked, and encouragingly, the ice does not seem to have returned. So touch wood, that won't be a problem in the future. Okay, so these are the first science images. So a big chunk of these released, I think, November last year, and then another chunk released in May this year. So I thought I'd just show these because it really kind of demonstrates the power of the thing. So this is a globular cluster, NGC 6397, and there's a Hubble Space Telescope image for comparison, just to show you the difference in scale here. So these are huge images, and you can download these from the ESA website, and they're like I don't know, 300 megabytes in size. And you can really zoom in on these really fine details, and you see things which just aren't possible, hadn't been possible before. This is a famous cluster of galaxies called the Perseus cluster. Again, this is a beautiful image. Again, a huge image with a lot of detailed structure in it. So I think that's very cool. Just to show you the power of going into space, the reason why space is good for a lot of this deep universe, deep sky observational astronomy is that you're outside of the atmosphere. So you don't have the distortion of the atmosphere getting in the way. So you can see much more precisely and clearly. So here's a map of the Perseus cluster from a ground-based telescope, and we just overlay Euclid on top of this just to see the difference. And you see that with Euclid we get a lot more detail. We see a lot more galaxies, a lot more objects that can't be seen from the ground. I quite like this one. This is IC 342. Not a very catchy name. It's called the Hidden Galaxy because it's quite close to the plane of the Milky Way. It's visible in the southern sky with binoculars on a clear night, but it's difficult to see in the optical wave bands because it's obscured by the dust of the Milky Way. But with a near-infrared camera, you see through the dust, and you see this beautiful galaxy. It's one of the kind of largest galaxies on the sky, actually, but it's not apparent because of its location. But again, you see beautiful spiral arms, these kind of dust lanes running through here, and that's a really stunning image. This is the Horsehead Nebula, famous nebula. Famous Hubble images of this. It's in the Orion constellation. It's a region of active star formation. You see these kind of tendril-like structures coming up here. So these are magnetic fields, we think, that are kind of creating these tendrils emanating from this cloud here. There's a Scottish connection here, which I only learned earlier this year, actually. So this was actually discovered, this system, by a woman called Williamina Fleming, who's from Dundee. So this is, I think the discovery was in 1888, so she moved to America at a young age, actually, and was part of the kind of Harvard observatory team who made a lot of discoveries. So this is credited to her. I like this one as well. This is another vibrant kind of star-forming region. This is again in Orion, M78. This is about, well, the scale is 1,300 light years away, so relatively close compared to some of the deep sky stuff that we see. This is an hour of observing time, but again, beautiful structure. There's so many interesting things happening in this image, and I think this one image, we've only discovered 300,000 new objects alone in this picture. Okay, so in the final part of the talk, I'll just look to the future and describe some of the things that we hope to learn. So Euclid is going to it's making 20 observations a day, and it'll do that every day for the next 6 years at least, possibly longer. Each observation takes about an hour. It takes about 4 hours to download the data every day. You've got to wait until the right ground stations are on the right side of the Earth to make the link with the satellite. Ultimately, we'll have hundreds of petabytes of data. So a petabyte is like 1,000 terabytes? A terabyte, 1,000 megabytes. So these are very, very vast amounts of data. So this is a data processing challenge as well. Obviously, no one computer can analyze all that. So we had to spread out this data processing across, I think, 8 data centers, mostly across Europe, one in the US as well. And each of them gets a chunk of the sky to process, and then it all gets assembled at some central hub somewhere. So as I say, we started full survey operations, and we just scan the sky. It looks something like this. We just take little square patches, and move on, and then do the next bit, and eventually we'll have a big chunk of sky. But so far, I think we've got about 500 square degrees processed. It's increasing all the time, of course. Don't spend too much time looking at this, but if you want to know the time scale of this whole mission, so as I say, it's about a 6-year mission. but there will be periodic data releases to the public and the science community. The next big one is in March next year. It's a relatively small patch called the Q1 release. So in March next year, there'll be a big chunk of Euclid data dropping. And then our major first data release happens in June 2026, which is about 2,500 square degrees. Then every couple of years we'll have further data releases, and then finally the third one in about 6 years' time or so is like our 15,000 square degree release. Okay, so I won't say too much about this. I've already sort of covered, made the point about this being a huge data processing challenge. Just wanted to say that in the UK, our science data centre is in this building here. This is one of the buildings on the site of the Royal Observatory. It's in this Higgs Centre for Innovation, one of the new buildings up on the site. And I thought I'd show the team here. This is not all the team, this is just the people who were around on that day. But it's a very it's a dynamic team with students involved and senior people involved, engineers, software developers. So it's it's been a really good experience, I think, to work on this. So just a sort of couple of ending points. So this is a mission to measure dark energy and answer one of these most fundamental questions that we have about the universe. So we want to know, is dark energy evolving, for example? Or is it static? Is it like the energy density of the vacuum? Or is it something different? The most simple expectation for dark energy is that it's something to do with the vacuum of space. But there's this big famous discrepancy between a prediction for the energy of the vacuum that you would make from particle physics and the observed acceleration. There's this huge discrepancy, so there's obviously stuff that we don't understand there. A connected question is to do with gravity. So, a lot of the physics I've shown you in that simulation is assuming that our theory of gravity is correct. It's assuming that Einstein's general relativity theory holds. But do we know that it holds? Do we think it really holds when we're talking about galaxies attracting other galaxies that are, many, many light years away? It could be that this acceleration problem is really something to do with the fact that we've got the theory of gravity wrong and perhaps we're not interpreting the data correctly. So that is a possibility, so-called modified gravity, so we want to test those ideas as well. I didn't say too much about neutrinos, but we want to measure the mass of the neutrino, this fundamental particle that has an impact and changes the way the structure forms. We want to know the initial conditions of the universe. Are they more complicated than we currently think? What was really going on in those early phases just after the Big Bang? So this is my final slide. So just to sort of summarise, the next 6 years is going to be very exciting for cosmology. Euclid, this is a fantastic mission, a lot of UK involvement, and we're going to get over 1 billion galaxies in total to measure the statistics of galaxy positions and shapes through this weak lensing effect, make maps of dark matter. And then, when we've got all the data, we should be able to make some pretty firm statements about the nature of dark energy and fundamental physics. So I think I'll just stop there, and thanks very much.
Okay. Well, thank you very much. That was absolutely fascinating.
Thanks.
So, does anybody get any questions? Bob?
Given the fact that Euclid obviously has a much wider field of view, how does what the JWST is finding out about early galaxies relate to this, in the fact that they seem to be much more developed at an earlier age than current theory would predict? Is there a link between the two instruments in terms of how you share data?
Yeah, good question. So the answer is not really, in terms of a connection between the data sets, because they are such diverse, if you like, quite different kinds of data. As you say, James Webb is taking relatively small fields of view, and especially in the infrared, and out to sort of much greater depths. Whereas Euclid is kind of looking more at the kind of recent universe, and over larger fields of view, so it isn't kind of picking up the fine detail that James Webb is. So they're quite different. And there's a question about whether data from Euclid could shed light on this question of what is happening with galaxy formation at early times. I think that's something that people are thinking about, but it's not quite clear at this point, because this problem has only really started to come out with the web results, and it's still kind of crystallizing. So I'm not sure. Certainly the kind of primary science goals are quite different, but we do learn something about dark matter, for example, and the way that dark matter is clumped on small scales. Perhaps that can say something about the way we predict dark matter to clump very early on. Maybe that's enhancing galaxy formation, and maybe that's kind of accelerating the evolution of those early galaxies. Yes, I would say there is probably synergy, but it's still being explored.
Okay, what corollary, if I may, you used the analogy of a swimming pool in your diagram, and you said, look, you can see that the water's having an effect on the tiles. Now, we know what the tiles look like when the water's not there. There's the data. But you don't have that data here, do you? How are you, you sort of, what's your baseline, if you see what I mean?
So we do have a similar prior expectation, which is that galaxies should be randomly oriented. So if we think of galaxies as like little disks, we think that they should just be randomly pointing in different ways. There should be no preferential alignments. But gravitational lensing will give you alignments. If light from galaxies are passing through the same foreground structure, you do see these alignments, and that's how you infer the presence of the dark matter. So there is that analogy, I think, with the swimming pool, in the same way that the tiles on the ground are, we understand the symmetries, if you like, of those tiles. In a similar way, we understand the kind of symmetries of galaxy orientations. They're basically random.
Thanks.
How do you compare your results to the Gaia system? The Gaia system does seem to be quite similar to yours.
Yeah, so Gaia is really focused on our own galaxy and measuring the positions of stars in our galaxy. Of course, Gaia also has galaxies outside the Milky Way too, but it's really optimized to get the stars. So Euclid is more interested in other galaxies outside the Milky Way. So we purposely avoid looking at the Milky Way entirely.
I hadn't realised that, but there is obviously a correlation of some sort between the two projects.
I'd say the science goals are quite distinct though, and that science goals have driven the different technologies. As I say, Gaia is more focused on kind of nearby stuff and understanding the way the stars move around our galaxy. And Gaia does answer questions about dark matter as well, so there is a synergy there. And at the observatory, we've got a lot of people working on Gaia as well, and we're always trying to understand, can the questions we ask about dark matter, how does it relate to the questions that the Gaia people ask about dark matter? Yeah, so they should be the same.
It's taking time.
Yeah.
Yeah, the back, yeah. Yep.
Does Euclid have anything to contribute to the crisis in cosmology?
Are you referring to the Hubble tension? Yeah. It will do. It's not designed to do that. It's something that it can do because it can measure the Hubble constant. It's not going to be as precise though as other methods. So I'd say that it will have something to say about it, but I don't think it will be giving us the answer.
So you mentioned that one of Euclid's first images was a short exposure. What counts as a short exposure for these types of telescopes?
Our normal exposure is about it's about 10 minutes, and it's repeated several times. I think the exposures I showed you before are maybe less than 10 minutes. But not more than that.
Yeah, up the back there. Yeah.
Is the rate of expansion started to increase 7 billion years ago? Is that just, are we just attributing that to dark energy? And I guess another question, Is there any other popular theories apart from dark energy and dark matter to explain the stuff that we don't quite understand yet?
Yeah, so, I mean, this acceleration, I say dark energy is what we have invented to explain this, but we don't know if dark energy is real. And if it's not real, it could be that the theory of gravity is wrong. That's another explanation. There are other more kind of wacky ideas out there. In the early days, people thought that we might be just living in a part of the universe that was relatively empty, and so things were kind of moving away from us just because they were being sort of gravitationally pulled onto more distant structures. But now we don't think that's really happening. I would say it's very uncertain. We don't know yet. Dark matter is a bit more on more of a solid ground because it's been around for longer. The idea has been around about 100 years now, and we think dark matter is some kind of new particle. That's called the leading theory. Is that it's a new particle that just hasn't been detected yet. And the reason that's the leading theory is because we know that there are lots of particles out there, and the 20th century was full of discoveries of new particles. That said, we've not found any new particles for a long time. The Large Hadron Collider failed to find any genuinely new particles. So yeah, there are other ideas out there to do with dark matter, but the current leading theory is that it's some new particle.
Yeah, Bill.
Just a simple question. You talked about the database being measured in terms of petabytes. How does that compare with the Gaia database?
Good question, and I'm not sure I know the answer to that. So Gaia measures like 1 billion stars, and for every star it's got a lot of information. So it could be comparable. A lot of that 100 petabytes is data that's processed from other telescopes as well on Earth that kind of form part of the Euclid analysis. So that's not all Euclid data. So I'm not sure what the answer to the question is. I imagine it's
I know that Gaia's huge. But
certainly comparable challenges. Yeah.
If I could ask you a sort of space-related question, I noticed that you were talking about it freezes up and you're losing the vision. So is that going to be a kind of regular kind of housekeeping thing that they'll have to do, is to every so often point the telescope towards the sun to kind of heat it up again?
Well, we don't know yet is the answer. So far, the ice hasn't come back, so there's no need to do that. If it does start to come back, then we will need to do it again. But it's quite disruptive to do this, because every time you heat the telescope up to get rid of the ice, you change the optics of the telescope.
Right.
And it takes a few days, even a few weeks, for things to settle down again. And in that time, the data is not really usable. So we lose observing time every time we have to do this. So hopefully, we don't have to do it periodically, but we don't know yet.
Right. Yeah. Thank you.
Can I ask a question, if that's okay, about the visible light imaging camera? In traditional broadband astrophotography, you'll have a monochrome sensor behind either a colour filter array of red, green, blue, or individual red, green and blue filters to assemble that full colour image. But I think you said you had high quality optical images using 8 colours?
Yes. So Euclid only has 4 filters. So the other 4 are coming from the ground-based telescopes. So there's like dedicated imaging from several ground-based telescopes that top up that 4 to 8. But it's all processed in the Euclid pipeline. So the Euclid, the visible image is just one broad band, and the near-infrared camera is 3 filters. So we've relatively sort of few filters for a mission like this, but with that broadband we do get a lot of light, so we do get very good detections of faint objects.
Okay.
I just wonder how you arrive at the mass of the neutrino.
Mm.
Given a small telescope out in space, a smaller by cosmic rays compared to what we do on Earth, where it's very a mile, 2 miles down,
Yeah.
massive tanks of argon detectors. It just seems
Yeah.
completely opposite.
Yeah. So the answer is that we don't make direct detections of a neutrino. So it's not like these ground-based things in mines that are trying to actually measure a neutrino flying through. We are really looking at galaxies and trying to understand and measure the neutrino mass via its impact on the pattern of galaxies. So it's almost like it's like a statistical measurement that uses the whole map of galaxies to understand what the mass of the neutrino is. The idea is that if you have a theory or one of these computer simulations, and those simulations will have neutrinos in them, if you dial up the mass of a neutrino, what will happen is that it will change the detailed pattern of structure in that simulation. So again, by measuring, taking our data and comparing to the simulations and sort of dialing this knob, we can read off the mass of the neutrino. Yeah.
Yeah. Thank you.
Just statistics, just statistics.
Just statistics.
You showed us the effects of cosmic rays hitting the imager. Do you measure the energy of the cosmic rays? And how long have you got left before the imager's closed?
Yeah, so the number of cosmic rays will increase with time, and of course we're at a solar maximum right now, so the amount of cosmic rays is high, unexpectedly high. So far, the damage to the detectors is minimal. We don't see any damage, but we do expect there to be damage over time, increasing and accumulating with time. I think the energy can be worked out based on the length of those little streaks. So I think people have tried to do that. But yeah, over time, we do expect to see the silicon in the detectors degrade due to the constant bombardment of these rays, and we get coronal mass ejections as well. When we had the aurora, the big aurora event that we had a few months ago, we were getting X-ray flashes and high energy particles hitting all the time. And every time that happened, it would basically we'd get an X-ray of the inside of the telescope. So we get all this kind of harshness of the radiation environment, and it's just going to build up over time, and we just have to live with it.
What practical applications could you foresee for the kind of answers you're putting together?
So I think, in terms of some of these questions, dark matter, dark energy, it's hard to say because these are very kind of fundamental, kind of blue skies type questions that are really about kind of fundamental stuff. So it's not obvious what the practical applications of that may be. There's no telling what they may be in the future. If we do learn something about fundamental physics out of this, that will underlie future technologies, because that's what fundamental physics does. There are practical applications of a lot of the technology that's been developed, though. All the data processing techniques that we use, distributing data across multiple nodes around the world to process stuff, that's all, a lot of that stuff is very novel, and that's got very clear practical applications. Likewise, a lot of the satellite technology that's been built and the optics has a lot of sort of practical use. So a lot of kind of there's a lot of added value, if you like. So there's stuff in here for romantic thinkers who like to sort of dream about dark matter. There's also stuff for people who want to see kind of practical applications and benefits to economies as well.
So you're on a 6-year journey after which you hope you'll have a data set to be able to make some statements about dark energy. but you don't work on something like this without entertaining some fancies. So, do you have any kind of predictions for what you're expecting to see, or things you'll hope to see about what dark energy actually is?
Yeah, that's a good question. So for dark energy, I would hope to see. So I like the idea that dark energy is really like some new physics. It's like some new field that is evolving as the universe evolves. Something a bit like the Higgs field that has the Higgs boson as its particle. It'd be very cool if the dark energy turned out to evolve in a way that looked like a new scalar field. And because that way we can then learn about the kind of very different energy scales of the universe that are very different from the ones that we normally probe. I think that we might just find consistency with Einstein's cosmological constant, which was this thing that he wrote down. So Einstein, when he wrote down the equations of general relativity, 100 years ago, had a term in those equations, the cosmological constant, that was he put in there because it can be in those equations and it all mathematically makes sense, but he sort of scored it out very quickly because he thought, oh, this can't be real. It'd be cool if that was real, I think. But yeah, the implications for that is still unclear.
Oh, I've got one at the back.
Hi, I understand Euclid to be very much a European project. I understand the field of cosmology can't really come to Russia anymore. So what effects have you seen on the project and cosmology in general now that Russia's come out of the picture?
Yeah, good question. I suppose the most direct impact for Euclid was that Russia pulled out of the French Guiana spaceport where it operates its Soyuz rockets from. Because the original plan was for Soyuz to be used, so that kind of delayed the launch of the satellite by about a year. I think more generally though, it's interesting because in the 20th century, a lot of the main results, the main breakthroughs in cosmology happened in the Soviet Union, and I think because there was this I don't know, I'm not an expert on the history of this stuff, but because there was this community in the West, and because this community in the Soviet Union who were sort of working on the same problems but completely independently, that did actually lead to some breakthroughs because there was this diversity of thinking. And nowadays, a lot of the best Russian scientists are working in Western countries, and that's where all the kind of money is. It's where the best facilities are, and I think your question is making me think, and I'm not sure. Yeah, I'm not sure I can really give a kind of very informed answer, but I feel like it will be having an impact on the ability of younger Russian students, for example, to travel to Western countries to study and give seminars and kind of be part of this kind of global community. So I think it is having this kind of probably is having this detrimental effect on human progress in this field for sure.
Okay, well, thanks everybody for coming along tonight. It's been an absolutely fascinating talk once again. If we could all give us a kind of I think we've got, I'm not sure, Dave, we've got more dark matter next month.
Yes, that's
Yeah, more dark matter next month. The amount of questions tonight is obviously a very interesting subject.